So we want first to show that Q is a probability measure and then that it is equivalent to P. Let's fix some lambda in the interval 0, 1. First we're going to check the four conditions that Q needs to satisfy in order to be a probability measure. Well, and to be equivalent to P. Okay, first, Q lambda greater than or equal to 0 for all elements of the sigma algebra F. And this holds since Q1 and Q2, two probability measures that make up Q lambda, are probability measures being multiplied by non-negative numbers. Second, Q lambda of omega, the entire state space, is equal to lambda Q1 omega plus 1 minus lambda Q2 omega, which since Q1 and Q2 are probability measures, these are both equal to 1, and we get lambda plus 1 minus lambda equals 1. Third, for any indexed sequence of sets which are contained in the sigma algebra F and are disjoint, we have that the measure Q lambda of the infinite union of all of those sets is equal, since Q1 and Q2 are probability measures. This should be a J from 0 really, indexed by 0, but of course could be 1 as well, it's equivalent. This is additivity. Oops. There we go. Additivity of those probability measures. And well, moving the lambdas inside the sums, combining these gets us to return to, that should be a J there as well. There we go. Q lambda of the OJs. So also additivity. So Q lambda is a probability measure, and we just need now that it is equivalent to P. Finally, for any A in F. First, Q lambda A equals 0 implies, since lambda and 1 minus lambda are both non-negative, that Q1 and Q2 of A is equal to 0. And since Q1 and Q2 are both equivalent martingale measures, they are both equivalent to P. And this holds, therefore, if and only if P of A is equal to 0. All we need now to notice is that if Q1 and Q2 are of some set A are equal to 0, then Q lambda, so the sum of them two, is also equal to 0. So this implication goes both ways. Thus, Q lambda of an element of the sigma algebra is 0 if and only if P of that same set is equal to 0, and that is Q lambda and P are equivalent. Now part B. So Z1 and Z2 are by definition densities of the measures Q1 and Q2 with respect to P. So we can have, by definition, of Z1 and Z2 as densities with respect to P, it follows from this definition that Q1 of any set A is equal to the expectation with respect to P, which we shall write without, of course, it's possible to write with notation P there, but when no measure is given, it's assumed that it's just the measure that comes with the probability space. So by definition of these Z's as densities, these expressions hold for Q1 and Q2 of the set A, of any set A, element of the sigma algebra F. Then it immediately follows that Q lambda of that set A as the sum of lambda Q1A plus 1 minus lambda Q2A is equal, using linearity of the expectation of lambda times Z1 plus 1 minus lambda times Z2 multiplied by this indicator of A. This is true for any element A of the sigma algebra, and therefore the density of Q lambda with respect to P is given by lambda Z1 plus 1 minus lambda Z2, this expression inside the expectation that's multiplying the indicator. It then follows that the density process which is defined as the expectation of Z lambda given Fk has the following form. This is using linearity of the conditional expectation. And these expectations, these conditional expectations, we could write as the density processes of those individual densities, Z1 and Z2 for Q1 and Q2. Now finally we want to show that Q lambda is itself an equivalent martingale measure. Well, we know that it's a probability measure, and we know that it's equivalent to P, so we just need to show that it satisfies the martingale property. Well, that the risky asset under Q lambda is a martingale. First we'll note that since S1, what are we denoting it just by S? No, S1. Since S1 is a Q1 and a Q2 martingale, they're both equivalent martingale measures. It follows from the definition of density that we saw in part B that S1 multiplied by Z1 and S1 multiplied by Z2 are martingales under P. That's just using the property of Z1, Z2 as densities of Q1 and Q2. This can be proven, for example, using the, so it doesn't follow directly, it's not immediate, but it follows quite quickly using the conditional expectation, proving, as we have done many times in other situations, that a particular random variable is a conditional expectation using just the definition of conditional expectation, those two properties that it has to satisfy, then it can be shown that these two are again martingales under P. Since a linear combination of martingales is itself again a martingale, it follows that lambda S1z plus 1 minus lambda S1z, that's Z1, Z2, this linear combination, which is of course S1 multiplied by Z lambda, is again a P martingale. Thus, again using the property that Z lambda is the density of Q lambda with respect to P, Z1 alone is a Q lambda martingale. And as I mentioned, since we know already that P and Q lambda are equivalent, we have that Q lambda is an equivalent martingale measure.